Okay, I wanted to give you a little help on this challenge problem number 26 on page 38. And this is known as a piecewise defined function. And early in chapter 2, we will delve into these pretty deeply. We'll do quite a bit of graphing of these, but this is going to give you an early taste of the inequality version of a piecewise defined function. So I wanted to see what you could do with it, but I understand you've probably never seen anything like this before. So if you need to just watch this enough to get an idea and then go do it on your own, that would be great. So here's how this works. All right, it's one function. It's a g function, but it's really broken up into three different pieces. And what these are called off to the right, these are called domain restrictions. Okay, in other words, well, let me just give you an illustration with the red piece. Okay, so just think of this as y is greater than x plus 2. Okay, so if we just had that one inequality, just ignore this for a second. If I told you to graph y is greater than x plus 2, well, the first thing you would do is think about the boundary line, y equals x plus 2. Okay, y-intercept of 2, slope of 1. And because it doesn't say greater than or equal to, we would do a dashed line. Okay, so let me change my line type. Just a second. All right, and I'm going to make this one red, and we're going to do a dashed line. Okay? All right, for this first example, I'm going to do something that probably won't be necessary going forward, but I think it's good to illustrate how this works in the beginning. Okay, so again, we're just doing y is greater than x plus 2. So I've got my boundary line dashed, get my running start here. My dashed line, y equals x plus 2. And the greater than side, of course, I'm going to save the shading part for last, but we would shade above the line. Okay, now let's talk about this, because this is, I've had this question come up. What's this all about? Okay, well, this is called a domain restriction, and it says this. Instead of showing all of the boundary line y equals x plus 2, we're only supposed to show it for x coordinates on the line that are less than negative 2. Okay, so let's talk about that for a second. This represents the dot, the point on the line where the x coordinate is negative 2. The coordinates that are less than that are going this way. Okay, this is x coordinate negative 3, negative 4, negative 5, and so forth. If I go this way, the x coordinates are greater than negative 2. So I'm only supposed to show this line where the x coordinates are less than negative 2. Or in other words, the domain, that's another word for x, is less than negative 2. So what I'm going to need to do is I'm going to need to cut this line or delete it so that I only show the beginning, the right side of this line, if you want to think of it as the beginning, starting at negative 2 and then continuing on from there. And pretend like that's not an arrow. It's just hard for me to change it. That really shouldn't be an arrow there, because that's really an end point. All right, negative 2 is an end point, and it's going to continue on for x values that are less. So it's an arrow here and then an end point here. And since it doesn't say or equal to negative 2, and that means negative 2 isn't supposed to be shown on the line, then I'm going to put an open circle here. Okay? If it had said or equal to, then I would have made it a solid end point. Okay? And then again, we'll save the shading until we've got all the boundary lines drawn. All right, does that make sense? I hope so. Now let's change colors and we'll do the blue. Okay, so let's pretend like it said y equals x, boundary line. And again, it's going to be dotted. I was going to say dotted and dashed together, dotted or dashed, however you want to put it, since it doesn't say or equal to. So y equals x has a y-intercept of 0 and a slope of 1. Okay, so this time let's not draw the entire line. Let's just think about the two end points, because this tells me I'm only showing the line for x values that are between -2 and +3. All right, so here is y equals x. It goes like this, slope of 1. Well, here is where the x-coordinate is -2 on that line. So that's one end point. And notice I'm going to make this a solid end point because it says or equal to -2. So -2 is part of the line. And then y equals x, goes like this. But I'm stopping the right side of the line should stop where x is +3. And that's right here. Also solid because it says or equal to. So instead of doing y equals x, the line y equals x without any restriction just goes like this. It's diagonal, slope of 1 through the y-intercept, goes forever and ever. But this domain restriction basically cuts the line, and it makes it a line segment. So I'm going to make this without arrows, and we will turn it to blue. And try to line it up a little bit better. It looks pretty good. Okay, so once again, it's dashed because it doesn't say greater than or equal to. Solid on the ends because it does say or equal to. So -2 is part of the line that should be shown, and +3 is also an x-coordinate that should be shown. Okay, we just have one more, so let's turn to green and just think for a minute about y equals -x. Well, it's similar to this, but instead of having a +1 slope, it has a -1 slope. Still goes through the origin, but it does -1 slope. This domain restriction says don't draw all y equals -x. Don't show all of the x-coordinates. Only show the x-coordinates that are greater than 3. All right, so y equals x would travel like this. This is the point where the x-coordinate is 3 on that line. And since it's greater than 3, I'm going to leave an open circle. It doesn't say greater than or equal to. So this would represent the line showing x-coordinates that are getting bigger than 3. Okay? So the rest of this line, according to this, doesn't need to show. All right, so this is going to be a one-sided, an arrow on one end, like a ray. I'll change color. And it does this. So it's not all y equals -x, just the part of the line that shows x-coordinates greater than 3. Okay, so we got our boundary lines. Now let's take care of the shading. And we'll do the shading in different colors. Okay, so let's do the red piece. Greater than this dotted line. The line keeps going forever and ever, of course, and the shading should stay above the line. But for this piece, it basically stops right here. It stops just shy of x equals -2. And you don't have to go crazy about this, and you don't have to shade in different colors. Just wanted to illustrate. Okay, the blue shading basically picks up where the red, and this red keeps going forever and ever up. I just didn't want to shade over. Okay, So blue essentially picks up where red left off, stops at the blue line, and it shades forever this way. So again, it goes from -2 over to +3, all of this area. Okay, and then green essentially picks up where blue left off. Okay, so it doesn't get to that line, but blue did. So it's basically just picking up where blue left off, like I said, and stay above the line. Don't do like I did. I don't color very well. And something like that. And it just continues on forever in that way. Okay, and that's our final answer. Kind of cool. These are, again, called piecewise defined functions, and this is the inequality version of that. And I hope that helped. And if you have any questions on that, let me know.